Okay, question 6. We have a car, it's going into the sand, and we've got to show how it's travelling once it reaches the sand. We're drawing an arrow on the diagram, so this is my whiteboard version. So you can think of this in terms of the two wheels of the car. As the car is coming through along like this, it's going to be travelling in a straight line, of course, but when it gets to this stage, you can see this wheel, this part of the car, is going to slow down because it's on the sand, whereas this half of the car is still going nice and fast because it's on the road. So if you're going slower here than you are here, you're going to change your direction that way. You're going to move in this direction. So we're going to see the car doing something like that. If we were going to draw the normal, we'd see that this angle here was bigger than that angle there. And that's consistent with the idea that things will bend towards the normal when they're going into a material that's slowing them down. So for your first question, you're just looking for an arrow that's closer to the normal than the original arrow. It's going to bend in like that. Explain why it's a useful model for the refraction of light. Well, you can see here, can't you? Just as the car takes a bit of time, well, not time, just as the car travels into the sand, changes direction because it slows down. The same is true of light. When light enters a material that slows it down, it's going to bend towards the normal, it's going to change direction as a result of that. Specifically in the mark scheme, we're looking for you to say the light and the car, both of them will slow down when they're into the new material, and therefore you're going to bend towards the normal. It was key for this one that you mentioned the direction in which it was going to change. It wasn't enough to say that it was going to change direction. You needed to say it was bending towards the normal because it's slowing down. The second section, or part B, over here we have the classic diagram of the prism and the light refracting and dispersing out. So we had to explain the path taken by the light through the prism, and we had to do it in terms of refraction and wavelength. So they've scaffolded that a little bit for you. You know that your answer, which is for 3 marks, is going to include those two ideas. So we can see the light coming in here. It changes direction, it refracts as it goes into the block, and then it refracts again as it comes out. We're talking about white light, and one of the key things whenever we're talking about colours of light and white light is to mention that white light is a mixture of all the wavelengths. And that's a key thing, often forgotten, often not clear, particularly from the question, that you need to mention that. But if in doubt, whenever they mention white light, to do with the colours of light, mention that it is a combination of all the colours of the spectrum. That would have given you the first mark. You'll notice the red light is refracted less, it's changed direction less than the violet light. The violet light has changed direction all the way this way, the red light not so much. So you needed to say that, the red light is refracted less than the violet light. The reason for that is that the red light has got a longer wavelength. The violet light has got a shorter wavelength, so it's refracted more. So you can see here, white light is a mixture of the different wavelengths or different colours. In fact, it says ignore colours in this one because it's talking specifically about wavelength. You needed to make the connection that when we talk about colours, we're talking about wavelengths. Each wavelength or colour is refracted by a different amount. These short wavelengths are reflected more. Notice again how this wavelength is highlighted, it's underlined, so you needed to say wavelength to get that mark. But they have helped you out by saying you needed to explain it in terms of refraction and in terms of wavelength. There's your 3 marks there. And the final part, describe how the student could use the procedure in figure 8, develop it to search for evidence that sunlight consists of additional electromagnetic waves. So we've got this whole colour spectrum here. We need to show that there is a part of the spectrum outside of that, so stuff that we can't see. Well, that's not too bad to do, particularly if you remember way back when we studied this Herschel's experiment, because he was able to prove that infrared light was being produced here. The way that he did it was he put something that would be sensitive to infrared over here. He put a thermometer there. So he put a thermometer over here, excuse me, beyond the red end of the spectrum. The thermometer will heat up and the reading on the thermometer will go up. So that's showing that you're getting infrared radiation. So specifically on the mark scheme, it's over here. There we go. One for saying place the thermometer with a blackened bulb. You didn't have to say blackened bulb, but that's what they did. They painted the bulb with the thermometer black to absorb the radiation better. Beyond the position of the red light, so beyond the red light here where the infrared should be, and then the temperature should go up as a result. So the bulb of the thermometer, in case you're not quite sure, you've got a thermometer that looks a little bit like this-ish, sort of. It's got kind of a lumpy bit at the end. You tend to have the red line rising up there. I'm just going to say mercury. These days we usually use spirits instead of mercury. Yeah, this is the bulb, and they painted it black so that it would absorb all or more of the infrared, because of course black objects look black because they absorb the radiation better. Good, that is the end of that question.